Okay, hello class. So today we're going to be going over some of uh, some of the example problems from the homework. So first we just have a supermarket attendant, and they are going to be pushing a can of soup, say to the back of a shelf because they're stocking. And in this case, they all we have to do to find the work done by the supermarket checkout attendant on this can of soup is we have to use our work formula for work is equal to FD. In this case, the force is going in the same direction as the can of soup. So then, in this case, cosine of theta is going to be equal to 0, or it's going to be equal to 1 because they're pointing in the same direction. So the angle between them is going to be 0. And so then our equation just reduces down to from FD cosine theta to FD. And so all we have to do is multiply the force times the displacement. And so another big thing is in this chapter we have to talk about units again. So we're going to be talking about a new unit that we're going to introduce called calories. And so 1 calorie or 1 cal is going to be equal to 4.184 joules. And so then 1 kilocalorie is going to be equal to 4.184 times 10 to the third joules, or 4.81 kilojoules. So, let's see, this is a 6. Excuse me. Okay. So all we have to do to convert our answer from joules here to kilocalories here is we have to take our answer in joules. So I'll put a little line here, joules, and then we have to multiply it by our conversion factor. So then we have 1 kcal is going to be over 4.4186 joules. And so then all you have to do, and then this is all you have to do, and then this will yield your answer in kilocalories. Okay, so next up we're calculating the work done on an elevator by its cable to lift it 40 meters at a constant speed where friction is averaged by 100 newtons. So we have our elevator here, and it is going up 100 meters. So this will be our D in this case, where it's say that this is 100 meters. And we'll say that the force of friction F, let's say this is 150. Actually, screw numbers. Let's do this without it. So this is D. We have our force of friction that gets exerted on the side of the elevator. And the elevator has some sort of mass, or some value for mass. And so all we have to do, we find our work is going to equal F d cosine theta. And so then this is just going to be equal to mg plus our force of friction multiplied by the distance that it travels. So we know what g is, we know what m is, we're given what f is, and we have d. So in order to do this, f in this case is going to be f net, and so we would do f net is equal to, and then we would, on our free body diagram, we would say, all right, weight is downwards, and since the elevator is moving up, there is a force of friction also downwards. And so then both of those are in the same direction. And so the work done is just going to be those two quantities added together times the distance that they are applied over. And so now we're talking about just what is the work done by gravitational force in this process. And so then we just have that W is going to equal negative mgh. And so then we just plug in what m is, we know what g is, and then we know what h is. This is going to be, h is just going to be the distance. And so what is the total work done on the lift? So we know that this is at constant speed. And so in this case, F net is going to equal 0. And so then in this case, the total work done is going to be 0 joules. Okay, so now we're going to talk about work in a more general point of view. So in this case, we're going to say, all right, well, we have F dot dr is our formula for work. And so we're dotting two vectors together. And so then this is just the magnitude of both vectors times cosine theta. And so for if you're given the magnitude of F and R and theta, this is the equation you'll use. And if we're given the components of F, what we have to do is we have to say, we can do this two ways. We can go ahead and retrieve the magnitude of these two, or you can use the other dot product formula that we learned in chapter 0, I believe, and we can say that this is going to be equal to f of x delta rx plus f of y delta ry, and this will also yield the same value as if you went ahead and said, well, f is equal to the square root of fx squared plus fy squared. And so now we have f for this, and then delta r is going to be equal to the square root of rx squared plus ry squared. And then what you would do is you would take theta is equal to the inverse tangent of ry over, or delta ry over delta rx. And that should give you the angle over which this is applied. And so then you would just plug these back into the original formula, and that should also get you the same answer as doing this. This is simpler and takes less steps than this one, but I'm showing you that there is a way to work through this problem. There's another way to do it. Okay, so next up, we have a box, mass M, is being pulled like this with some angle theta here. This is going to be F, and we can find our coordinate axes as Y and as X. And so all this question is asking is, at the beginning, this is going to be equal to 0. All this question is really asking is to define an expression. So it's kind of breaking it down into its steps. So it's finding an expression for the work done on this object. We've gone over this just previously, where W is equal to F dot D. And so then this is going to be equal to FD cosine of theta. And so next up, they just have you using this formula and plugging in numbers. So just plug in your numbers. And so next up, they want us to do what is the speed of the box at a distance d. If the surface is frictionless, we know that Fx is going to be equal to F cosine theta. And that this is also going to be equal to max. So then ax is going to be equal to F cosine theta over m. And so then we just have to use our equation Vf equals Vi squared plus 2a delta x. So in this case, this is going to be 0 because we defined our initial velocity. And then so then we just get that Vf is going to be equal to the square root of 2a and ax delta x, because we just have to plug in that this is the x component of the acceleration. And we can go one step further by plugging in our value. So this is the square root of 2f cosine theta delta x all over m. Easy peasy. Okay. So next up, we have a box being accelerated along the floor at a certain value for acceleration. And so we are just given that it's along the floor. So then all the values are going to be in the x direction. So we have this box with some acceleration a. And so they give you now a time period of t, and they want to find the network in joules. So one thing that we can do is we can bust out our old kinematic equation for A, which is going to be Vf minus Vi all over T, where T is going to be equal to Tf minus Ti, but we're going to assume that at the beginning this is going to be equal to 0, and so then we're just going to get that T is equal to Vf over A. And so from this, we're going to be able to find what Vf is using the work energy theorem. So W is going to be equal to is going to be equal to delta K here. This is going to be equal to 1/2 mv f squared minus 1/2 mvi squared. And so since our initial velocity is equal to 0, this is 0. And so then we have to just, all we have to do is we're given T. I don't know why I did this here. I've been trying to solve this the wrong way. But VF is going to equal AT. And so then we can plug that in here like this. And so that work is now 1/2 m a squared t squared. Okay, so now we're talking about an airplane taking off. And so the airplane produces a certain thrust and this force is going to be equal to some large number, and we have a very large mass as well. And so it needs a certain number d, and it's going to be some number in kilometers. So this is going to be kilograms. And so first things you need to know is we have to convert kilometers to meters so that it's a actual useful value. And so all we have to do is we have to take the number that we're given and tack on a times 10 to the third, and that will solve our problems here. So now we want to find what the takeoff speed of the jet is, so the velocity that it achieves when it takes off. We do something very similar to the last problem, kf minus ki for our work energy theorem. When it starts its acceleration, or the thrust is turned on, it has a velocity of 0, so ki is equal to 0. So then we have Fd is equal to 1/2 m VF squared, where VF is what we're solving for, so VF is going to be equal to 2 Fd over m square root. And so that should yield the final velocity here. Okay, and so next is a very, very, very theoretical question. So in this case, we're using a giant spring with a K constant that is enormous. And in this case, we know that the potential energy of the spring is equal to work. We did that last time. And so we have 1/2 kd squared is going to be equal to Fd, because this is going to be our potential energy is equal to our work. We did that last time. And so all we need now is to solve for d. So we're asking how far do we need to compress the spring in order for it to launch the plane at the same speed that we derived here in order to launch this plane into the air. So all we have to do is we have to solve for d here, and so we can easily see that this is going to be equal to, or d is going to be equal to the square root of 2fd over k, and that will give you your distance in meters. Okay, so next up we have a skydiver jumping out of a plane, and skydiver has some mass of m in kilograms, and they fall a certain distance in meters before opening their parachute, and they reach a maximum v in meters per second. So now how much in work in joules did air resistance do on the skydiver before she opened up her parachute? So we need to do a couple things in order to find find the work in joules that air resistance did. I covered this briefly last time, but so we're taking, this is going to be our y-axis, and so we're going to have our skydiver. We'll draw him as just a dot for now, and we have, this is W pointing downwards, and we have our drag force pointing upwards, so I'll write this as FD. And we know that, so the sum of forces then, or F net, is going to be equal to W plus FD. And I'll write this as a subscript here so we don't confuse it with work. And so one thing that we can do is we can say, all right, well, we can use our work energy theorem, where work is equal to delta K, which is equal to Kf minus Ki. And so now in this case, we have two contributions to W, the work done by gravitational force and the work done by air resistance. We have both those forces outlined here. And so then we know the one done by air resistance, WA, is going, this is the composite work, right? This is both of these combined. So we know that WA plus WG is going to equal delta K here. And so then WA is going to be equal to delta K minus WG. And so in this case, the delta Y is going to be negative because they are falling. So they're falling from a higher height to a lower height. And the force of gravity is going to be pointed in the negative direction. So this is just going to be equal to mgh. And we know what h is from what we described our d was. And so delta k in this point, or at this point, is going to be 1/2 mvf, as vi is going to equal 0. And so then we get that this is a negative sign in between them. And so we don't even have to use an equation for work due to drag force, because in this, by using the work energy theorem, we have solved for it using the work energy theorem and the work done by gravity. So now in this case, all we have to do is plug in our numbers here. And we can make this slightly simpler by factoring out an m, but realistically, you can just plug in what you have, because we have what v is as vf, we have what m is, we know what g is, 1/2 is just a constant or a coefficient, and we have h with respect to d. And so then we can find that work. So next up, since we have found the work of air resistance, or work done by air resistance, now they want you to find what the force was. So they want you to find this now instead of the work. And so all we have to do is we say that W is equal to F dot D. And so in this case, all we're going to have is that this is going to be opposite her motion. So cosine theta is going to yield us a -1. So then all we have to say is that work is equal to FD cosine theta, but we know that cosine theta is going to equal a negative value here. And so we can say that FD is going to equal negative W over D. And this should yield your force as what we've done from before is we found that this value here is going to be negative. So these are going to cancel, the negatives are going to cancel out here. And this is going to be a positive number. So we've then solved this problem. So next we have to talk a little bit about power. So the equation for power is quite simple. It's just the work done over time. And so in this case, we have that power is equal to W over T. And so this one's extremely simple because you are given what the work was and they give you what the time was that it's dissipated over. And so then you just have to plug the numbers in. And this one is super simple. Okay, so next up, it says that a pitcher supplies a power to a baseball of a mass for a period of time. And so one thing that it asks, it says, what's the ball speed in meters per second when it leaves his hand? So in this case, we know that P is equal to W over T. W is then equal to PT. Work equals power times time. And we know that W is equal to our work energy theorem. And so in this case, before the windup, that ball's velocity is going to be 0. And after the windup and he throws the ball, it's going to have that final velocity. So we can say that this is 1/2 mvf squared. And then VI was going to be equal to 0. And then we can say that VF, if I could write, VF is going to be equal to 2W over M all under the square root. We know what W was though, so this is equal to the square root of 2PT over M. And that will yield your final velocity. And last but not least, we have a large household air conditioner consumes some kilowatts of power during normal operation. So what is the cost? Now we're doing costs. Yeah, no, I'm not doing this one. You guys can go ahead and do this. Just make sure to check your units. You're looking for an answer in dollars here. So all of your other units at the end of the day should cancel out, and you should just get the cost for this. So in this case, just know that we have given a cost of electricity in kilowatts is we get some number of dollars per kilowatt hours. I gotta use a different marker. This one's ridiculous. So the cost of using this electricity is going to be dollars per kilowatt hours. And so they tell you how many, they say how many hours per day, so they 1 hours per day. And they give you the number of days. And so if you multiply this number, you'll get how many days out of or how many hours out of the month that so you just need to multiply these numbers together to get the hours that the air conditioner is run during this fill cycle. And so in this case, all we have to do, so that's, yeah, we got the time there. And so then you just need to multiply all three of your numbers together. So you are given how much power this consumes during a normal operation. And so you just have to multiply those three numbers together, and that will give you how much it costs to run that air conditioner for the month. Okay, I'm signing off here. Everybody have a great weekend, and study hard.